Okay. So, welcome to analog communication course. So far we have done some discussion about Fourier series and the representation of any signal, any periodic signal, let us say with respect to some known basis periodic signal like cosinusoidal or sinusoidal or exponential sinusoidal. So, this is something we have done. We have also done a simple example in the last class. So, if I just recapitulate that. So, what we have done is we had a signal like this which has a period of 2 pi. So, defined from minus pi to pi, and it is basically centered around 2 pi again and so on. So, it just repeats after every 2 pi and the strength is 1. So, this is our general signal which is Wt, let us say. So, while representing this Wt, we could represent Wt as exponential Fourier series. So, n going from minus infinity, I am just recapitulating the same results. So, it is dn e to the power jn 2 pi f0 t, where of course f0 is 1 by 2 pi, which is meaning that t0 is 2 pi. So, that is the period, and we have also evaluated our dn. So, that happens to be whenever n is not equal to 0. So, dn becomes 1 by n pi sin n pi by 2. So, this was our dn, and d0 was just half, right. So, this is something we have already done. So, eventually what we have got is something like this, a spectra which was defined in frequency domain. So, it was having value of half or 0.2 at 0, then at every f0, 2 f0, 3 f0 there are values. So, at f0 it is, if you just put at means frequency component 1. So, that is n equal to 1. So, there if you just put this, you get 1 by pi and so on. So, at 2, so this was at 1, at 2 you got 0 and so on. It was going into negative, again 0 and so on, and it is symmetric. So, at minus 1, minus 2, something like this. Okay. So, this is what we have got. If you see carefully that our this dn term is now a real number, all dn including d0, these are real number. So, initially what we have told that dn can be a complex number, and the amplitude of that is plotted in amplitude spectrum and the phase of that is plotted in phase spectrum. Because the dn's are all real, and so the dn d minus n. So, basically what happens, the phase part is always 0. So, the phase spectrum will nothing but will be just 0 everywhere. So, it does not have any phase part, right, for all the frequency component. So, for every other frequency component starting from means the DC value which is at frequency 0. So, it has a half. So, that means you, if you wish to plot this, it should be something like this, all the basis function. So, d0, so that is in time if we just plot. So, that is actually half strength DC, where the strength is half, times 0 minus infinity to plus infinity, it is defined as this. Next is at frequency 1 Hz. So, it is a sinusoidal, or we should say cosinusoidal, with amplitude 1 by pi. So, all we have to do is we have to draw a cosinusoidal of frequency 1, that means the period is 1. So, basically, so this part, if this is 0, this must be 1 and so on, it repeats after every this one. So, the period is 1, and what happens basically the strength should be 1 by pi as we have got. And remember, because the phase is 0, so the cos actually starts from here only, 0 phase. cosinusoidal. So, always whenever you are actually constructing these signals, you have individual constituent of this same signal. So, basically signal has been decomposed into multiple either DC value and all other orthogonal cosinusoidal. So, we are just trying to plot those cosinusoidal. Now, what is happening, you should also remember that this particular cosinusoidal, if you see it from here, because it is an exponential Fourier series. So, this part is actually making the e to the power j 2 pi, that f is now 1. Okay. So, basically it is at 1 this is defined. So, f will be 1 over here. So, it is this, right, and you have a corresponding cosinusoidal at the negative frequency. So, that also you will have to put. So, and because the dn's are for both the cases 1 by pi, so it becomes 1 by pi e to the power minus j 2 pi t, and then if you just add these two, what you get is actually a cos with strength 1 by pi. Okay. So, that means the frequency of it is 1 and the strength is 1 by pi. So, basically whenever I am plotting this cosinusoidal, you need to understand that we are taking a positive frequency and the corresponding negative frequency, taking both the amplitude as well as the phase information. So, if you see over here carefully, we were actually taking the amplitude information and putting it over here, because the amplitude is even symmetric amplitude spectrum. So, we will have same value over here. So, modulus of dn will be put over here and the phase of dn will be means put over here, okay, plus and minus. So, that is the phase part, because here the phase is 0. So, we do not see the effect of phase, but otherwise the phase effect should be there, and the corresponding cosinusoidal that will be happening, that will give you exactly the amplitude as well as the phase information. So, cos will be either lagged or leading by that amount of phase. So, this is what you have to do whenever you are trying to draw the corresponding basis signals. You have to take from the amplitude signal the amplitude, and you have to take phase from the phase spectrum. Okay. So, these two information you have to take and you have to draw the basis signal. Similarly, the second one will also come over here. If you see the second one has amplitude 0 at frequency 2, right. So, of course, the time period will be that 1 by 2. So, basically what will happen, this has a higher frequency. So, it will actually repeat within this. Okay. So, the thing will be at a higher frequency, but because the amplitude is 0, you will not see this, because it is a cosinusoidal where the amplitude is 0. So, the third constituent is non-existent. The fourth one, if you see, it has an amplitude which is negative. So, accordingly cosinusoidal will have a negative sign in front of that. So, the cosinusoidal will start at a pi phase shift. So, it will be looking like this, and the frequency of that will be 3 times. So, you start putting the 3 times frequency within this, and you keep doing that. As you go along the frequency line, your frequencies will be doubled thrice or 4 times, and accordingly the repetition period will be shrinked, and you will have to draw those things with exact phase and amplitude. Once you draw this, and if you add all of them up to infinity, you will see that exactly the signal that we have targeted will be generated. So, this is the significance of it. So, basically what we have done is we have taken a periodic signal, we could represent them with respect to corresponding cosinusoidal or DC value, and the specification that is required is completely contained in that dn. So, dn basically gives you two information, one is the amplitude information and other one is the phase information. For every frequency, whenever you specify n, that means it is n into f0, that fundamental frequency. So, n into f0, at that frequency what is the corresponding amplitude, that will be the modulus of dn, and the phase of dn will be the corresponding phase. So, you get these two and then you plot it, and whenever you are plotting, you are actually putting a cosinusoidal. So, you are taking two values from the spectrum, as we have already explained, that it should be always, because it is a real signal. So, it should always take a in exponential Fourier series, one from positive and a corresponding negative. So, these two together will generate your cosinusoid, that is what is happening. So, and you will be getting, as long as you are having that complete amplitude spectrum and complete phase spectrum, for every frequency term you will be getting corresponding amplitude and phase, and accordingly you draw the cosinusoidal and you add them up. If your phase and frequency, phase and amplitude informations are correct, that means dn you have correctly evaluated, you will always, if you sum all of them, you will always get your signal back. This is what is happening, that every signal now is decomposed into all the harmonics of it, and every harmonics is defined for this particular targeted signal, is defined by its specific amplitude and specific phase. Okay. So far so good. We know now what is the utility of Fourier series and how Fourier series actually represent a signal in a different domain. So, it is actually we are representing the signal in frequency domain. So, we are almost seeing the frequency component or the sinusoidal component of that signal which constituent this particular signal. Okay. So, this is all good. Now, we have talked about a measurement of a signal, right, initially in the first few classes. So, we have talked about energy of a signal. So, if the signal was real, we have told that the signal has to be squared and integrated over the time that it is defined. So, let us say it is defined from A to B. So, as long as signal Gt is a real signal, this is what we will have to do, and we get the corresponding energy of the signal. This is something we have defined, that squaring the signal and then integrating over the time that it is defined. Now, if the signal is not real, that it is a complex signal, then we have to specify another term, that means you have to take the modulus of that signal and square it. So, basically you have to do this mod Gt square dt and you have to integrate. So, same thing you have to do, but for calculating, evaluating the energy, because it is a complex signal and energy is a real number. So, we need a real number. So, we have to do we have to take the signal, we have to do a complex conjugate of that. This is all something we have defined. By definition, this must be the energy, right. So, this is something we have told already, that this is a measurement of a signal. Like we have done that vector analogy. So, in vector it is the distance of the vector or the strength of the vector, which is also means measured by distance square, right. So, this is how it is being measured. Now, if we just say for any signal we want to basically get the energy value of that signal, right. It is very easy, take that signal, integrate it over the time that it is defined. So, suppose we have that square pulse, right. So, remember it is a periodic signal. So, definition of energy, we have already talked about periodic signal where it becomes a power signal, right. So, the definition of energy is not there, but if we just take the definition from minus pi to pi, then it is an energy signal, and then within this we can still define the energy of this signal. So, if you wish to calculate the energy, what you can do, you can just integrate from minus pi to pi g square, right. If this is my signal, you can integrate. Is there any other way, or in the frequency domain can we also talk about this energy representation, or can we just say that this particular signal we have already identified that it is means defined by multiple basis signal and their linear combination, and the coefficient of them are already known via Fourier series, right. So, if we just take this signal and take those constituent, is there a possibility of defining the energy from that perspective? So, in the frequency perspective, every component how much energy it actually provides to add up to give this energy. Is it possible? So, that is something we will be now exploring. So, let us try to see what happens to this. So, before that, let us say I have two signal xt and yt. Okay. To my definition, these two signals are orthogonal to each other. So, I am just trying to exploit that orthogonality property and energy calculation. Okay. So, we are just assuming that two signals, very simple two signals which are orthogonal to each other. It might be just like cos omega ct and sin omega ct. We have already proven these two signals are orthogonal within a particular period, right. So, if it is defined from minus pi to pi. Okay. So, take these two signal and let us say I wish to generate another signal zt, which is just an addition of these two signals. Now, my target is, so I am almost going towards linear combination of orthogonal signals. So, right now I am just giving a very simple example that I have got two orthogonal signal, I am just adding them. It is a linear combination with coefficient 1, right, plus 1. So, I am just adding these two signal. Now, we wish to see, suppose for xt and yt, I have already evaluated the energy of them. So, this is suppose Ex and this is Ey. I have evaluated the energy of that. So, how I have evaluated x and y, if means I do not care if they are complex or if they are real. So, I just have done this xt modulus square integration dt over the period that it is defined. Okay. So, a to b. So, for our case, if xt is cos omega ct, so minus pi to plus pi. Okay. So, this is something I have evaluated and this gives me Ex. Similarly, for y also I have done the same thing. So, I have done a to b yt modulus square dt, that gives me Ey. Suppose I know these two parameter Ex and Ey, both of them. Can I now calculate the energy of zt without actually means adding them, integrating and all those things. So, does orthogonality gives me some idea of these things. So, let us try to see. So, energy of zt, what does that means? A to b modulus zt square dt, right. So, that actually means a b, now it should be xt plus yt modulus whole square dt, right. Now, expand this. So, that should be mod xt whole square plus mod yt whole square plus xt y star t plus x star t yt, right. This whole thing integration over dt, right. So, now you can see this particular part mod xt whole square dt, that is actually Ex for us. This part is the Ey for us. Now, the orthogonality plays a big role. What is the integration under t over that period as long as xt and yt are orthogonal signal? We know that that term should be 0. That is the property of orthogonality. Any orthogonal signal, if you take that signal and take the complex conjugate of that, multiply that and integrate over the period that you are targeting or where the signal is defined, it will be always, as long as xt, yt are orthogonal, that should be always 0. So, this term happens to be 0, this term happens to be 0. So, basically what we get is the energy of z is just the summation of energy of x and y. This is a very fundamental results which has big implication. Okay. So, we will try to use this and try to prove a very fundamental theorem which is called Parseval theorem. So, let us try to see if now from this, if we just go to a linear combination of orthogonal signal. So, suppose I have a signal, let us say xt, that is defined as some linear combination with coefficient ci xit, where all the xi's are orthogonal to each other. Okay. So, that means that if you take cross product, so x1 with x2 t star and you integrate over the particular targeted period, you will get 0. Okay. So, these are all xit's are all individual orthogonal signal, and this I goes from means to its limit, as many i's are there. Okay. So, over I you have to sum. Okay. So, if this happens, what we can get, if you see, so the energy of xt, if we just try to calculate this, that must be, we know that it is a, just take the previous example. If you have two orthogonal signals to each other, it will be individual energies square or individual energy addition of that, right. So, if I try to calculate the individual energy. The individual constituent is, suppose let us say I starts from 1, so or 0. So, let us say starts from 1. So, C1 x1 t, what is the energy? If we know that x1 t has an energy of E1, okay, already. Therefore, that C1 x1 t will have an energy of, you have to integrate modulus of this. So, C1 into C1 star, so that should be mod C1 square, that will go out of the integration. So, if I just do that, C1 x1 t, C1 star x1 star t dt integration. So, C1 star will be mod C1 square, this integration x1 t x1 star t dt, that is the energy of x1 which is E1. So, it should be mod C1 square E1. So, that is the first term. So, it should be the first term should give me the first energy component, and similarly all other energy component. So, there will be C2 mod square E2 plus dot 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 up to as many i's are there. All cross components, because the signals are orthogonal to each other, will be just vanished. So, I can always evaluate, as long as I can represent a signal with respect to the constituent orthogonal signal and their linear combination. If I know all those coefficients, I can always evaluate the energy of the original signal. This is what was targeted, and I can do that. Now, let us apply this to Fourier series. Let us see what happens. So, in Fourier series, what has happened? Any signal xt, a periodic signal of course, that has been represented as n equal to minus infinity plus infinity, we are taking the exponential Fourier series formula. So, that should be dn e to the power minus plus j 2 pi n f0 t, right. So, that is the representation, we have already seen that, and dn must be evaluated as done by Fourier series, right. So, this is something we have already seen. Now, what we are saying is this, that here as long as we know dn, we know that for every n these are those orthogonal components, right. So, therefore, the energy of x must be the individual energy, where the coefficients are, it is a linear combination of these orthogonal signal, right. Each of those orthogonal signal, what is their corresponding energy? So, if I just take e to the power j 2 pi n f0 t and I wish to evaluate its energy. So, what I have to do? I have to take this signal, I have to do a complex conjugate j 2 pi n f0 t dt integrate over a period, let us say minus pi to pi. If I just do this, this will give me 1. So, I get 2 pi, right. So, this is what I get immediately. So, I know that if this is a particular signal and I wish to evaluate its energy, so I can always evaluate it like this. And of course, whenever we are evaluating this energy, it also has 1 by T0, if you remember the signal means the way the signal has been evaluated. So, the corresponding dn term will always have 1 by T0. So, that 1 by T0 will come. So, 1 by 2 pi will come, this will give me 1. Okay. So, that will be always giving me 1, so because this 1 by T0 or 1 by T0 means 1 by 2 pi, that will be there. Okay. So, I have to evaluate this way the energy 1 by 2 pi minus pi to pi, we have to do this, right, and I get individual energy of those signals as 1, right. So, this is something I get. So, once I have got this, then I know that the overall energy should be just individual, suppose the 0th term is d0. So, mod d0 square plus, then I have to get d1, d minus 1, everybody's mod square. So, d1 square plus d minus 1 square plus dot dot dot. Now, I also know that, of course, remember that this coefficient square into the energy of the first one. Okay. Now, the energy of the first one is for any value of n, that is 1. So, that is why all those values are coming to be 1, right. So, what do we get? Overall energy is just the summation of this coefficients. So, I can either write them as n equal to minus infinity to plus infinity mod dn square, or I can, because I know these two are symmetric. So, I can write it as mod d0 square plus 2 into n going from 1 to infinity mod dn square. I can also write this way. This is the famous Parseval's theorem. Of computation of energy of a particular signal. So, basically what has happened, if I had a signal xt, I was aware of its energy. So, that I can do in a very simple way, that okay, take the signal, integrate it from within a period. So, let us say minus pi to pi, I can do that, that is one way of doing it. But because I know the Parseval's theorem, what I can do, if I know the Fourier series representation of this signal, that just means that all the dn's I know, I have evaluated all those dn values. So, once I know all those dn's, the energy of the signal is also can be also be represented in a different way. That means all constituent signal, all constituent means orthogonal signal, you take their coefficient and take a modulus of that, make square, add all of them, you will get the energy of the signal. So, basically it is just very simply understandable that a signal, if it is already there, you have decomposed into multiple basis signals, and each of those basis signal has their own energy. Okay. So, the energy is dependent on the corresponding coefficients, that is dn. So, as long as you know the dn, you can take modulus square, you get your energy representation of that particular constituent signal, and because the signal is linear combination, you can just take linear combination of this energy or addition of this energy, I should not say linear combination, addition of these energies, that will create the overall energy. What exactly is this? If you just take it from vector analogy. So, we have already done a vector analogy to signal. So, what is happening, if you have in vector, we already know that if a particular vector is represented by linear combination of two vectors, then what should be the strength of this vector? That must be, through Pythagoras theorem we know, because these two are orthogonal. So, that must be this square plus this square, right, and this square is the actually strength or measurement of that vector. So, measurement of this vector plus measurement of this vector must be the measurement of this vector, as long as the measurement is distance square. Okay. So, if that is the case, and if we are talking about Euclidean space, we can always see vector measurement, which is distance square, is just the vector measurement of the corresponding component in, means when represented in orthogonal vector space, right. Same thing is happening over here. If you see what is happening, these dn's, so whatever dn we are putting over here, these dn's are actually the measurement or the coefficients of the corresponding orthogonal signal that constituent this signal. So, as long as we know this dn's, we can get corresponding energy, which is actually again the measurement of that particular signal or the energy of that particular signal. So, measurement means energy over here. So, energy of that particular signal. So, we get energy of all constituent signal, and it is just the addition of those energy which gives me the overall energy of the signal. That is the strength of Parseval's theorem. So, basically Parseval's theorem state almost similar thing as we have got in vector space. So, all the cross terms are vanished because they are orthogonal, similar thing happening like vectors, and only the corresponding measurement add up to give me the measurement of the signal, and our measurement is energy. So, in the next class what we will try to do, after getting this sense of signal, we will try to think about a signal which is continuous in time, that is true, means in a way, but most importantly if it is a non-periodic signal or a energy signal. What to do, what kind of treatment we should take for those kind of signals will concern, means we will concern ourselves about that only. in the next class.